All right, welcome back everyone for another deep dive.
Excited to be here.
Yeah, me too. And today we're going to be looking at something called Proofgold.
Ooh, that's a fun one.
Yeah, so it's cryptocurrency,
Of course it is.
but it also uses formal logic.
Formal logic in cryptocurrency, okay.
Yeah, so we're going to be taking a look at excerpts from this paper,
All right.
Proofgold, blockchain for formal methods, and yeah, we're going to try and figure out what this is all about.
I think people are going to be surprised.
Yeah, like how can you even put those two things together, right?
Yeah,
It's like oil and water, you know?
it's a very strange combination, but it's quite fascinating how they've managed to do it.
So what is Proofgold?
So Proofgold is a peer-to-peer cryptocurrency network, much like Bitcoin,
Okay.
but instead of just tracking transactions of currency,
Yeah.
it's actually tracking things like publishing theories, defining objects, proving theorems, posing conjectures,
Whoa.
all on the blockchain.
So like a public ledger almost of mathematics.
Yeah. A public record that can't be tampered with?
That's so cool. Okay.
Yeah.
So how is that different from just like Bitcoin or any other cryptocurrency?
Well, the math is a big part of it,
Okay.
but it's also how it combines things.
Right.
So Proofgold uses a hybrid consensus mechanism.
Okay.
It combines proof of stake
Okay.
with proof of burn.
Just a burr.
Proof of burn.
What is that?
So your influence on the network is based on how much Proofgold you own,
Okay. Like proof of stake.
just like proof of stake.
Yeah.
But you also need to burn small amounts of Litecoin to participate.
You're destroying other cryptocurrencies
You are.
to make this one work.
Yeah. It actually links Proofgold's security to Litecoin's proof of work system.
Wow. Okay.
It's a very strange system, but that's part of what makes Proofgold unique.
So this is like a side chain, kind of almost.
Yeah, you can actually see an outline of the Proofgold blockchain from the Litecoin blockchain.
That's so cool.
Yeah.
Okay, so we've got the secure, math-focused blockchain. But how does the logic actually work? The paper mentions something about, and I'm just going to read it here,
Go for it.
intuitionistic, higher-order logic with functional extensionality.
Oh, yeah.
I have no idea what any of those words mean.
Well, that's a mouthful, isn't it?
Yeah.
Basically, think of it as a language with specific rules for creating and manipulating logical statements.
Okay.
So you have building blocks like types, which define categories of things. You have
Wow.
terms, which represent objects. And then you have propositions, which are statements that are either true or false.
Okay.
And so these come together to express those logical and mathematical ideas in very precise ways.
So almost like a programming language in a way, but for math.
Kind of, yeah, you can think of it that way.
Okay, that's cool.
Yeah.
So are there any limits to this logic system? Like, can you express any mathematical idea within Proofgold?
There are some practical limitations.
Okay.
For example, proofs can't be too large
Right.
due to block size limits.
Right.
They also can't be too complex to check.
You-
You could end up with something called a poison proof, which takes forever to verify.
Oh, wow.
So it's a delicate balance between being expressive and being efficient.
Right. You don't want to clog up the whole network with some, unsolvable problem.
Exactly, yeah.
Okay, so we've got this logic system that's running on the blockchain, but what about the software itself? Is there like just one program for interacting with Proofgold?
So there is Proofgold Core, which is the original client software.
Okay.
But as the blockchain grew, it started experiencing performance issues.
Ah, the classic growing pains.
Exactly.
Yeah.
So to tackle these challenges, one of the paper's authors actually developed Proofgold Lava.
Okay, so Proofgold Lava is like the new and improved.
It is. It's faster and more stable.
Cool. So what did they change?
Well, they made some pretty key improvements. For one, they switched to a more efficient database system,
Okay.
which drastically sped up data retrieval and operations.
Makes sense.
They also implemented a more robust and flexible cryptography layer, allowing for options to use the well-tested Bitcoin crypto implementation or a potentially formally verified cryptography library.
Wow, so they're really focusing on security here.
Yeah.
Okay, what about the other parts of the software, like the networking, the proof checking? Did any of that get upgraded as well?
Oh, yeah. They optimized a lot of that, too.
Okay.
So they streamlined the communication between nodes on the network and also optimized the process of verifying proofs,
Gotcha.
which makes the whole system much smoother and more robust.
So this is really a big step forward from that original Proofgold core.
Oh, absolutely. Yeah.
Okay, cool. So I'm really curious about this whole bounty system.
Yeah, the bounties.
Yeah, we kind of touched on it earlier, but how do these bounties actually work?
So in the early days of Proofgold,
Okay.
for the first 5,000 blocks,
Hmm.
half of the block reward was automatically allocated to bounties.
Okay.
These bounties were for proving randomly generated propositions.
So this was to encourage early adoption.
Exactly. It was a way to incentivize development and kickstart the process of proof development.
Gotcha. Okay, that makes sense.
It was a very clever way to do it.
So how hard are these bounties?
Well, they varied.
Okay.
Initially, those bounties were generated from the built-in HF theory.
HF theory.
HF theory, yeah.
Okay.
Which focuses on hereditarily finite sets.
Okay.
But now, the bounties are generally based on much more advanced mathematical concepts.
Okay.
They're drawn from, like, established textbooks and stuff.
So they've gotten harder.
Oh, yeah. They're much harder now.
Okay, so how do you even go about proving one of these bounties?
Well, there are tools that can help.
Okay.
One of them is called HOL4. It's a powerful interactive theorem prover.
Mm-hmm.
And one of the paper's authors actually developed a special interface between HOL4 and Proofgold,
Okay.
specifically for tackling bounties in that HF theory.
That's cool, all right.
Yeah.
So are there different approaches to proving these bounties?
Yeah. There are two main approaches.
Okay.
One is manual, and one is automated.
Okay, so manual, you're just like pen and paper, like figuring it all out.
Pretty much you analyze the bounties formula, you break it down, and then use logical deduction
Mm-hmm.
to prove it step by step.
Okay, gotcha. And what about this automated approach?
Well, the automated approach uses a tool called HOA hammer.
HOA.
HOA hammer, yeah.
Okay.
It translates the problem into a format that external automated theorem provers can understand.
Okay.
And so these are powerful systems that can often find solutions much faster than a human could.
So it's like a math bot, basically.
Yeah, you can think of it that way.
That's cool.
Yeah,
So are there challenges even with using these automated tools?
absolutely. One major challenge is the size of the proofs generated by these tools.
Right, because we talked about that before.
They can be huge,
Yeah.
sometimes exceeding Proofgold's block size limit.
Right, because everything has to fit in a block.
Exactly.
Okay, so even with all this advanced technology, you're still working within the constraints of the blockchain.
All right, it's always a balance between computational power and efficiency.
Okay, so we've gone pretty deep into the weeds here
Yeah.
with like the logic and the bounties and the software, but let's zoom out a little bit.
Okay.
What is the big picture here? Like, what is the potential of this whole system beyond just like solving math problems and getting some crypto?
Well, that's where it gets really exciting.
Okay.
Imagine a world where we can incentivize the formalization of important mathematical theorems and subproofs on a massive scale.
So we're talking about building a library of verified math knowledge.
Exactly, yeah.
Wow.
And because Proofgold is decentralized,
Right.
this knowledge base can be accessible to anyone, anywhere.
It's like a public library of math, but it's all been verified.
It's constantly being expanded and refined by a network of contributors.
This is amazing, okay?
Yeah.
I need to know more about this.
We've only just scratched the surface.
Okay, well, hold on to your hats, listeners, because in part 2, we're going to dive even deeper. Welcome back, everyone, for part 2 of our deep dive into Proofgold.
Yeah, we're ready to go even deeper.
Yeah, last time we were talking about the potential of Proofgold to create this massive library of verified math knowledge.
Yeah, that's right.
You even mentioned that it could revolutionize how we approach these large-scale formalization projects, but
Yeah.
what would that actually look like? Like, how would that work in practice?
One of the things that really struck me in the paper was this idea of using Proofgold to formalize the classification of finite simple groups,
Okay.
which is this monumental theorem that took decades
Wow.
and a huge team of mathematicians to prove it.
Yeah.
Imagine if we had Proofgold back then.
So you're saying we could have cracked this problem much sooner if we had this technology?
Yeah, it's a possibility.
Wow.
Imagine being able to take that project, break it down into smaller chunks,
Okay.
smaller bounties within Proofgold. Mathematicians from all over the world could contribute.
Right.
They could prove individual pieces and then gradually assemble the complete proof.
So it's like crowdsourcing a math proof.
Exactly.
That's wild.
Yeah.
Okay, so back to the technical side for a moment.
Okay.
You mentioned before that one of the paper's authors actually published a theory within Proofgold specifically for reasoning about syntax.
Right.
What does that even mean?
So this is where we start to see the applications of Proofgold in computer science,
Okay.
specifically in program verification.
Program verification, okay.
So instead of just proving theorems about, abstract mathematical objects,
Right.
we can start to prove things about code, making sure that it behaves exactly as intended.
Wait, so you're saying we can use this to prove that software is bug-free?
Potentially, yeah.
Wow, that's huge. How does that even work?
So this theory utilizes something called higher-order abstract syntax.
HOAS.
Higher-order abstract syntax.
HOAS.
Higher.
And it's used to represent syntax with binders. Binders, like the things you put paper in?
Not quite.
Okay.
Think about binders in programming
Yeah.
as things like functions or loops,
Yeah.
where you have variables that exist within a specific scope of the code.
Mm-hmm.
HOAS allows us to represent these structures formally.
So it's like you're describing how the code works.
Exactly. It's a very precise way to represent the logic of code.
Okay.
And one fascinating example is how they use this HOAS theory to publish conjectures about the existence of certain combinators.
Combinator.
Combinators, yeah.
What are those?
So combinators are essentially building blocks for functional programming.
Okay.
They're like functions that operate on other functions.
Oh, okay.
And the fact that they were able to publish and prove conjectures about these combinators within Proofgold shows how it could be used for things like verifying the correctness of programs.
So like making sure that the program actually does what it's supposed to do.
Exactly.
That's super powerful.
Yeah, it is.
Okay, so back to these math treasure hunts, these bounties.
Yeah.
Are they all just these abstract mathematical problems, or are there different types of bounties?
There's definitely a variety.
Okay.
The paper actually outlines 8 different categories of bounties.
8 different categories.
8.
Yeah.
Okay, so remember those early bounties that were automatically generated from the HF theory?
Yeah.
Well, they were categorized,
Okay.
and they added some structure to all the chaos.
All right, give me the rundown.
So you have the random category.
Okay.
Those are just random bounties, not really meant to be meaningful.
Just like throwing stuff at the wall and seeing what sticks.
Yeah, more about pushing the limits of those automated proving systems.
Got it.
Then you have quantified Boolean formulas, or QBF bounties,
Okay.
which deal with problems often found in computer science. You've got set constraints bounties, which are all about sets, finding solutions that meet certain criteria for sets.
Okay, so this is getting a little bit more complex.
Yeah.
Okay.
We also have higher order unification, which is a core concept in logic and computer science.
Okay.
Untyped combinator unification, which deals with those building blocks for functional programming that we talked about earlier.
Right, with the combinators?
Yeah, the combinators.
Okay.
And then you have abstract HF problems, which are essentially problems about hereditarily finite sets.
Okay.
But they don't rely on all the usual assumptions.
So this is like really testing the boundaries of the theory.
Yeah, exactly.
Cool.
Then you have aim conjecture problems,
Okay.
which are based on an unsolved problem in mathematics.
Oh, wow.
So these are unsolved.
So it's not just proving things that we already know, but like potentially discovering new knowledge.
Exactly, yeah.
Wow.
And finally, we had Diophantine modulo and Diophantine bounties,
Oh, okay.
which deal with a type of equation that has fascinated mathematicians for centuries.
Oh, wow. So it's a pretty diverse range.
Oh, absolutely.
Okay,
So-
so what's the actual process for claiming a bounty?
It's a race to the finish line,
Okay.
but there's a catch. Remember those proof size limits we talked about?
Right.
Those come into play here.
So you can't just submit a massive, complicated proof.
Exactly. There's a trade-off between finding a proof that's small enough to be accepted by Proofgold
Okay.
and finding a proof that's actually, both correct and elegant.
So it's not just brute force, it's got to be clever.
It's about finding that elegant path to the truth.
I like that.
Yeah.
Okay, this is all so fascinating.
It is.
We've only got one part left. I'm not sure we're going to be able to cover it all.
Don't worry, we'll tie it all together.
Okay, well, stay tuned, listeners, because in part 3, we're going to wrap it all up. All right, welcome back for the final part of our deep dive into Proofgold.
I'm excited to wrap this up.
Yeah, me too. I think this has been like one of the most mind-blowing deep dives we've done.
I know, right? It's such a fascinating concept.
So last time we were talking about like all these different potential applications of Proofgold.
Mm-hmm.
We talked about building this verified library of math knowledge.
Right, like that huge library.
Yeah, and even verifying the correctness of software.
And remember, it's all decentralized.
Yeah, which is crazy.
Which is huge. That's what makes it so unique.
So you've mentioned a few times this idea of changing how we approach scientific collaboration.
Yeah.
I'm really curious to dig into this a little bit deeper. Like how would Proofgold actually change how researchers work together?
Well, think back to that example of classifying finite simple groups.
Right.
That was a massive, massive project.
Yeah, decades.
Decades, tons of mathematicians all working together.
Yeah.
Imagine if Proofgold had existed then.
So you're saying we could have solved that like way faster.
It's a possibility,
Right.
right?
Wow.
Think about breaking down a project like that into smaller bounties within Proofgold.
Yeah.
Mathematicians from all over the world
Right.
could contribute their expertise,
Mm-hmm.
prove individual pieces,
Mm-hmm.
and then you slowly build up that complete proof.
So it's almost like crowdsourcing.
Exactly. Crowdsourcing a mathematical proof on a global scale.
That's crazy.
And because it's all tracked on the blockchain,
Yeah.
it's transparent, it's immutable, so you can actually see the whole lineage of the proof.
Yeah, that's a good point. It's not just about speed, it's also about like transparency and verifiability.
Exactly. Anyone can contribute.
So it's like democratizing access to this really complex math.
Exactly.
That's awesome. Okay, so beyond math, what other fields could benefit from this kind of collaborative approach?
I mean, the possibilities are really endless.
Yeah.
Physics, computer science, economics,
Wow.
any field that relies on that rigorous proof, that logical reasoning.
So Proofgold is almost like a proof of concept for this new way of doing science?
Yeah, I like that.
That's really cool.
It's more open, it's more collaborative, it's
Right.
driven by a shared pursuit of knowledge.
It's amazing.
Yeah.
So as we're wrapping up this deep dive,
Okay.
what is like the one key takeaway that you want our listeners to kind of walk away with?
I think it's important to remember that Proofgold isn't just about cryptocurrency. It's not just about mathematics.
Mm-hmm.
It's really about human ingenuity.
Yeah.
It's about collaboration.
It's about working together to solve these big problems.
Yeah, it's finding new ways to leverage our collective intelligence.
This has been a wild ride.
It has.
I'm walking away with a whole new appreciation for Proofgold.
Me too.
And I hope our listeners are as well.
Yeah, and who knows what other crazy discoveries are out there.
Yeah, like maybe Proofgold will inspire other innovations.
That would be great.
Yeah.
I think that's a great place to end it.
Okay, well that's it for our deep dive into Proofgold.
It was the good one.
Yeah. Thanks for listening, everyone, and we'll catch you next time.